several other descriptive statistics in a series of videos that discuss central tendency and dispersion. So these next two videos are going to focus on central tendency. And this is the value or values in which our data tend to cluster around. And oftentimes we think about this as the average, but an average is only one type of measure of central tendency. We're going to discuss both in this video and in the next video. So let's think about some data. Maybe we go out and we collect herring and we measure their length to get an understanding of the typical length of these fish, and we're interested in the central tendency of our particular sample. Well, we can measure the mean, which is the average. We can look across males and females. We could measure the median, or we could measure the mode. In this particular lecture, we're going to focus on the mean. In the next lecture, we'll talk about the median and the mode, but these are likely terms that you're familiar with and comfortable calculating. If not, no worries. We're going to talk about each one of them and we'll do some practice in class. So, the goal for a measure of central tendency is to produce a single number, and this is going to be a statistic. It's going to represent our typical measures of our data. And again, there's several measures of central tendency: mean, median, and mode, and each one has advantages and disadvantages. Some are more appropriate than others based on the characteristic of a data set, based on a sample. And so it's going to be important for you to pay attention to these strengths and weaknesses, and when to use these appropriately. So we've got our three main measures of central tendency here: mean, median, and mode. And again, this video is just going to focus on mean. The next video will focus on median and mode. So the arithmetic mean, this is probably the most frequently used measure of central tendency in general and in statistics. And this is one that we're going to typically use for most of the semester, unless we're told otherwise. So the mean is simply the sum of the measurements of our data divided by the total number of observations. So we can use the following formula in which to calculate the mean of a population. So this symbol here, mu, represents the mean. Now this is a Greek letter. It looks a little bit unfamiliar, and so this should indicate to us that this is a population parameter. This is for the entire population rather than the sample. So we've got our formula: mu equals the summation of x, which is our data, divided by large N. And large N represents population size, so the total number of individuals within the population. And x in this particular case represents our data. So in order to calculate the mean, first we would take the sum of all of our respective data points for the entire population, and then we'd divide it by the total number of individuals within the population. Now, as we discussed in the beginning of the semester, measuring population parameters can be pretty tricky because we're oftentimes not able to sample every individual within a population. So oftentimes we use samples in order to infer patterns in populations, and so we use statistics. And the statistic that we're interested in this particular case is the mean. So we can make a slight adjustment to our formula here, switching mu to x bar. Now, any letter that has a bar over it is going to indicate that we are interested in the mean. So it doesn't just have to be x, it could be any particular letter. Also, another adjustment that we've made is that the denominator is now small n instead of large N. Small n will dictate the sample size as far as how many observations we have from our sample rather than the total population size. Other than that, the operation is exactly the same. We take the summation of all of our observations and then we divide it by n. So let's go through an example. Let's see how this works. So let's say that we're interested in the mean fork length of a particular type of fish that we've collected. We have our data here, and we can use our formula in which to study and calculate this test statistic, this mean. So first off, we'll go through and we'll take the summation of all of our respective data points. So we can take each one of our observations from the length column, we can add them together, we get the summation, and then we're going to divide them by the total number of observations. In this particular case, we have 5 different fish that we've measured. We then follow this operation and then report our mean size of our fish. We could also maybe take the mean weight of our respective fish. So in order to get some practice, pause the video now, use the formula, and calculate the mean weight of our fish. Okay, so in order to calculate the mean weight of our fish, we'll take the summation of our respective observations, divide it by the total number of observations, and then we can get our respective mean weight of our fish, some in the neighborhood of about 0.1 kilograms. One more example here. We can look at our abalone ring data. We can collect 5 different individuals. We can look at the mean number of rings. So we add up the total number of rings observed, divide it by the total number of observations, 5, and we get the average number of rings among our individuals. Now, note here that for each one of our respective means, we have a different number of values after the decimal place. The reason for this is that in statistics, it's really good practice to report one more significant digit in our output than the values that the data are used to calculate it. So in this particular case, our rings are whole numbers, so we are reporting our output one value past the decimal place. In order to make your calculations appropriate, key will be to not round your values until the end of your calculations, and you'll be using calculators and or computers to do so, so this shouldn't be too much of a problem. For more information on calculating the arithmetic mean, check out text section 4.2.4, and also I'd encourage you to work through and check your answers for practice exercises 4.1 and 4.2. Now, let's say that we go out and we are collecting data on the size of oysters, and we happen to notice that there are a variety of repeating values for our particular oyster sizes. Now, rather than going through the process of adding all of these values together, we can use a frequency distribution table to reduce some of our time for calculations and also to visualize the data at the same time. So we can go through and we can list all of the possible observations that we have from the smallest value to the largest value, and then include the frequency of these observations. Again, this will be the total number of observations for each one of these respective values. And then also making sure that we include the values that have 0 observations, that way we can keep things in order. And then we can calculate the relative frequencies either as a fraction or a decimal. This should be relatively familiar to us based on our video and our practice from creating frequency distribution tables. So we've got our data and we've got our frequencies. Now we can use the formula for mean in order to calculate the mean of this particular data set, but notice that we have one small addition to this, which is important, is this f value here in the numerator, and this is representative of the frequency of observations for each one of our respective values. So before we go through and calculate the mean of our respective data set, we need to calculate the product of x times f, so the frequency times the value of our particular observation. So we can go through and calculate that for our first observation, 3.3, 0 for the next observation because there were no oysters that were 3.4 centimeters in size, and then we can continually go through and calculate f times x. And then at the end, take the summation of this respective column. Now, once our data is in this particular format, it will be very easy for us to calculate the mean values. So one thing that you should become comfortable with is not only creating a frequency distribution table, but also using them to determine what the mean is for a particular data set. So this numerator is going to be the summation, which is 95. Our denominator is a little bit challenging to understand at first, but after we go through this example, you'll see that it should be relatively straightforward. Now, we may be tempted to say that small n equals 13 because we have 13 possible sizes of oysters, but in fact this is not true. What we're interested in is the summation of our frequencies. These are the total number of observations that we have in our data set, which is 24. After we've determined that our numerator is 95 and our denominator is 24, it's just a matter of calculating out the quotient. In this particular case, our mean oyster size is 3.96 centimeters. Again, noting the fact that we add one additional significant digit, one significant figure after the decimal place compared to the values we use to calculate this, which have one significant digit, 3.3 centimeters, 3.4 centimeters, and so on. Now, this particular mean is known as the weighted mean. The reason for this is that some of our data points have a greater contribution than others, and so they have a stronger weight. And so in this particular example, the sizes 3.8 to 4.1 tend to occur more frequently. They've got a stronger weight. So we can use this formula with a frequency distribution table to more easily calculate the mean. So what I would like for you to do is to use the following frequency distribution table and to calculate the mean size of blue crabs. So take a moment, pause the video, and you can work through this. Okay, so first step for doing so will be to determine our small n. To do so, we take the summation of our frequency column. In this particular case, it's 48. We then need to go through and calculate the product of our frequencies and our observations, f times x, and then we'll need to take the summation of this particular column. In this particular instance, it's 1883. We then simply take our numerator, divide it by our denominator, and then we can report the mean size of our blue crabs. This is our weighted mean. For more information on this, we'll be calculating these in class, but also check out sections 4.2.5 in the text, and as well as go through practice exercise 4.3. Now, the mean is incredibly useful, and it's something that we will be applying to many of the statistical tests that we will use throughout the semester. However, there are some issues with the mean. Now, let's say that we have two different data sets. We've got two different samples, y and y star, and each of the first 5 observations are exactly the same. So in this particular case, the mean would be exactly the same. But let's say that we collect one more individual for each sample. And in this particular case, those individuals are quite different from one another. And as a result, our means will be quite different from one another, simply because of this last observation, y6. Now, this last observation, particularly for our y sample, not the y star sample, is much different than the rest of our data. And this very obscure or very distant value is considered an outlier. Now, outliers we discussed briefly when we talked about pie charts, and this is going to be a term that you'll want to be familiar with. The mean can be significantly impacted by these extreme values, these outliers, these observations that are quite distant from one another. In this particular case, our mean would have been exactly the same if we'd only considered observations y1 through y5, but in adding y6, the mean of our sample y was much larger than that of y star. And so here we've only got one value that's different, but it's significantly changing the means of our respective values. And so depending on if we have outliers or not, the mean may or may not be most appropriate. And we're going to discuss this moving forward when we talk about the next 2 measures of central tendency, median and mode, in the next video.